Good morning. To start with, I'd like to talk about the definition of the definite integral. This is going to let us work several different types of problems, including problems involving areas, volumes, surface areas, work, also other types which we may look at depending on how the time goes. To begin with, I'm going to assume that my function f that I'm looking at takes on only positive values, so that the graph is above the x-axis, and that the function is continuous. There are no breaks or holes in the graph or anything like that. These two conditions don't really need to be true for all x's, just the ones I'm interested in. We'll think of starting at x equal a and ending at x equal b. When we say that we're going to form a partition of the interval from a to b, what I mean by that is I'm going to start at a, which I'll call x number 0, and having selected some positive whole number n, I'll call b x number n. In the middle, I'll have x1, x2, x3, x4, and so on, which get steadily bigger as you increase the index. The width of one of these subintervals is going to be the x-coordinate of its end, for instance x1, minus the x-coordinate of the beginning. It's the x-coordinate of the right-hand end minus the x-coordinate of the left-hand end. So delta x number I will be x number I minus x number I minus 1. Now, there is some logical development to be done here, so I'm not going to be able to finish the sentence just yet. We'll have to talk about some stuff. Within each subinterval, there's going to be a special number that I'll call gamma number I, so that something happens, but at this moment we can't finish that sentence. If I just look at subinterval number I, it starts at x number I minus 1 and ends at x number I. There's a certain amount of area to go with that. The way I've got this drawn, the biggest function value happens at the right end and the smallest at the left. That isn't necessary for our discussion, but it's good for visual representation. Obviously, the area under the curve is smaller than the area of this rectangle, which has the same horizontal length as our original region did, but its vertical extent is the biggest function value that you can get on subinterval number I. Also, obviously, the area of this region is bigger than the smallest function value times delta x number I, for the same reason. When I write minimum over interval number I, I'm just thinking of that particular subinterval. So the area is smaller than the biggest function value on subinterval number I times its width, and the area is bigger than the smallest function value times delta xi. Since lengths are positive, I can divide through by delta xi and not mess any inequality signs up. This is a function value in subinterval number I. This is another function value in subinterval number I. If f is continuous, then every number between the maximum and minimum is a function value. So this tells me that ai over delta xi is a value of the f function for some x number within subinterval number I. So I'm going to call that x number gamma number I. A number I over delta x number I is f evaluated at gamma number I for some interval, for some gamma that is, gamma I, within subinterval number I. This is the end of that sentence, or equivalent to it. Now, I want to emphasize this is an exact mathematical equality, so if I want the total area under the curve, I can just add up all these different contributions. This is the area of subchunk number 1, the area of subchunk number 2, and so on and so forth. So you can end our sentence officially now. The area is exactly the sum of f at gamma I times delta xi, where gamma I is an x number within subinterval number I. Of course, we don't know exactly where those gamma numbers are. We just know that they are within certain subintervals. What comes next is asking a lot, but suppose this happens. You set up one of these partitions. You let the norm of the partition be the biggest of the delta xi's. For each subinterval, pick an x number, not necessarily gamma I, just one of the ci numbers. Form the sum of the function values at the various ci's times their corresponding delta xi's, and then take the limit as the biggest length of a subinterval tends to 0. That is to say, as the individual subintervals shrink down to points. Suppose this limit exists regardless of the details. By the details, I mean exactly how you've laid down these partitions and exactly how you pick these CIs. Suppose no matter how you do it, as long as the widths of the subintervals tend to 0, that these sums approach the same number. We call such a function integrable. If you wanted, if you knew what the gamma i's were, you could make the gamma i's and the ci's the same number, and then the limit of this sum would be the limit of that sum, but this sum is the area under the curve from A to B. It doesn't depend on the partition. It's a constant with respect to the partition, having norm tending to 0. So therefore, if all of this miraculous stuff happened, if this limit exists, it has to actually be the area under the curve from x equal a to x equal b. The discussion that we've had only works or is only interpreted as an area problem if the function f is positive and continuous. It's possible that this limit of sum exists even if those things are not true. If the limit exists, which again in the positive continuous case you can interpret as area, if the limit exists, we're going to make up a symbol for this limit. We're going to call it the definite integral from a to b of f of x with respect to x. When you write out things, you should actually pronounce it this way in your head because it'll keep it straight that there's something significant going on here. This is the definition of the definite integral. You probably have forgotten all of this kind of stuff because it was covered in Chapter 4 of Calculus 1, and everyone was eager to get on calculating things. We're going to need to know this in order to do what we want to in Chapter 7. As a way of getting started on this, I want to remind you of a fact. If you take positive whole numbers, starting at 1, and ending at some other positive whole number that I'll call n, if you add up 1, 2, 3, 4, so on and so forth out to n, it turns out that that's always equal to n times n plus 1 over 2. As an example of this, 1 plus 2 plus 3 plus 4 plus 5. The first three numbers add up to 6. 6 plus 4 is 10. 10 plus 5 is 15. On the other hand, if n is 5, then n plus 1 is 6. N times n plus 1 over 2 is 5 times 6 over 2, which is 30 over 2, which is 15. If you take math reasoning, you will prove that this statement is always true. We're just going to make use of it. I want to look at the integral from 1 to 5 of 2x plus 1 with respect to x. Now, everyone has had Calculus 1, so you already know how to get the answer. An antiderivative for 2x is x squared. That is, x squared is a function such that when you do the derivative, you get 2x back. Plus, an antiderivative for 1 is x, and then using the methods that you did in Calc 1, we will evaluate that at the limits of integration and subtract 5 squared plus 5 minus 1 squared plus 1. In the end, you get 28 for an answer. If all I was interested in was calculating the integral, this is perfectly good, but this is not going to be what we're up to in this chapter. I want to investigate this from this awful definition of integral business. Also, I'm going to be as lazy as I can. I'm going to have the interval from a, which is 1, to b, which is 5, x0 to xn. I'm going to divide it up into smaller chunks. Each chunk is going to be the same width, so this will make life a little easier for me. So x1 is a certain distance from x0. x2 is that same distance away from x1. The entire width of this interval is b minus a in general, 5 minus 1 in this particular case. I'm going to think of some positive whole number n. It might be 7 or 15 or a million. I'm going to make delta x the width of the entire interval divided by how many chunks that I'm going to break it up into. x0 is a plus 0 times delta x. x1 is delta x more than x0 was, which was a. x1 is a plus 1 times delta x. x2 is delta x more than x1, so I'll take a plus 1 times delta x and add delta x to it. x2 is a plus 2 times delta x, and probably everyone sees what the pattern is. In general, x number I, using equally sized subintervals, is going to be a plus I times delta x. This is true for I equals 0, 1, 2, out to n. Also, the first subinterval starts at x0 and ends at x1. The second subinterval starts at x1 and ends at x2. The third one starts at x2 and ends at x3, and so on. If I pick an index I from 1 to n, having n subintervals, subinterval number I, chunk number I, it ends at x number I, and it started at the previous of the x numbers. Within each chunk, I'm going to pick an x number. I'll call it C number I. All I need C number I to do is to be somewhere in the interval that starts at xi minus 1 and ends at x number I. I could pick the left-hand end of the interval if I felt like it. I could pick the right-hand end. I could pick some x number in the middle. It doesn't make any difference because of the limit giving the same number regardless of the detail business. To be lazy, I'm going to make ci the same as xi, which is the right-hand end, which is a plus I times delta x, in general. In our specific case, we know some stuff about the a and the delta x. That is to say, a is 1, and delta x is b minus a over n, 4 over n. So c number I in our example is going to be 1 plus I times the number 4 over n. A, I, delta x. It's important that you get that pattern right. Now, I'm going to look at a sum. I'm going to take function values at the ci. I'm going to multiply by the corresponding delta xi, and I'm going to add up all of those things. F of x is 2x plus 1. What that means, not to insult anyone's intelligence, is this. The way you do the f procedure to a number is you double the number and add 1. In our sum, I have to look at f evaluated at ci. There is no x in that. The way you do f to the number ci is you take the number ci, multiply it by 2, and add 1. This expression is what's going to be my function value here. So if I actually write out literally what f of c is, it's 2 times x number I, which is 1 plus 4 over n times I, and then later add 1. If you multiply everything out in combined terms, f evaluated at ci is going to be 3 plus 8 over n times I. I have to multiply that function value by delta x, which worked out to be 4 over n. Then I'm going to add all of those things up. The sum, f at ci times delta xi, is the sum of these numbers times those numbers. There's often confusion about these summation symbols. What this means is I'm going to let I be the index from 1 to n, and for each one of those index values, I'm going to take the thing inside the bracket, put in the appropriate I number, and add them all up. So when I is 1, I'm going to be 12 over n plus 32 over n squared times 1. When I is 2, I'll have 12 over n plus 32 over n squared times 2. When n is 3, and so on and so forth. You see, you don't have just one term of 12 over n. You have a whole bunch of them. You have as many terms 12 over n as there are indexes that I'm adding up. So if I want to group things together, I'll group all of these things together and all of those things together. There are n of these things, and then when I add up the rest of it, it's 32 over n squared times 1 plus 2 plus 3 out to plus n. And now you can see why we wanted to remember that sum formula, because I'm going to need it right here. I'm adding n copies of 12 over n together. That gives me 12 over n times n. 32 over n squared, and 1 plus 2 plus 3 out to n is n times n plus 1 over 2. In the first term, the n cancels out, leaving me with a 12. Here, I can cancel a factor of 2 out. I'll have a 16 remaining upstairs. Also, I can factor an n out between the n squared and the n times n plus 1. After everything has been simplified, I get 12 plus 16 times the number n plus 1 over n, which if you want, you can go on and multiply out some more. N plus 1 over n is n over n plus 1 over n. N over n, of course, is 1. 16 times 1 is 16, plus 16 times 1 over n is 16 over n. So these sums that we're looking at, using equally spaced subintervals, choosing the CI to be the right endpoint, the sum is 28 plus 16 divided by n. Since the delta xi's are all the same number, namely b minus a over n, 4 over n in this case, making the delta x tend to 0 means the same as allowing the n to become indefinitely big. So when I want to take the limit as delta x tends to 0 of these sums, that's the same thing as taking the limit as n tends to infinity of those sums. Those sums, of course, work out to be 28 plus 16 over n. This is a sum of two numbers, one of which is a constant. The other one depends on n. The limit of a constant always exists. If the limit of this term exists, then I can simply write this limit as the sum of the two things and be done with it. 16 is constant. As n becomes indefinitely big, 16 over n approaches 0. Now, never say this. Never say the limit approaches 0. The limit is 0. It's these individual numbers that are approaching 28 plus 0. The limit is equal to 28 plus 0, which is 28. If you look back to the start of this problem, that's what we got by doing the antiderivative method. To finish this introductory section up, again, remember that in general, we define the definite integral from a to b of f of x dx to be this limit. If we decide to be lazy using equally spaced subintervals and also using the right-hand ends, we can write the sum I equal 1 to n of f at a plus I times delta x multiplied by delta x, where the delta x is the width of the interval divided by the number of subdivisions. This format is going to be convenient for us at times. It's going to allow us to do a certain problem that appears to be impossible to do unless you know about this sort of thing. So here's a problem. I want to evaluate the following quantity. The limit as n tends to infinity of the sum I equal 1 to n of 6 divided by n times the cosine of 4 plus 5i over n. This is not anything that we know about using any reasonable techniques. I see that factor of 6 over n. That tends to 0 as n tends to infinity, so that makes me think maybe the 6 over n is going to be the delta x when all the dust has settled. That turns out not to be right. Remember how this went? It was going to be the function evaluated at a plus I times delta x. If I think that way, a plus I delta x, and I look at my problem, there is a 4 plus I times 5 over n running around in it. I'm going to think of that as being the right-hand end of subinterval number I, and I'll make the identification that a needs to be 4 and delta x needs to be 5 over n. I also need to know what the upper limit of integration b is, but b is x number n, which is a plus n times delta x, which is 4 plus n times 5 over n, which is 9. So if I think of this as being the right end of subinterval number I, this tells me three things. It tells me the limits of integration, and it tells me the spacing. I still have to do something about that 6 over n there. 6 over n almost looks like delta x, except delta x is 5 over n. This is not a big problem. 6 over n is 6/5 times 5 over n. 6 over n is 6/5 times delta x. So start writing the stuff down now. I'm going to have a factor of delta x. I'll have this factor of 6 over 5. I'll have a cosine of c number I. Usually when we write these kind of sums, we write the delta x down at the end. So I'll put the factor of delta x there, and what's left is 6 over 5 times cosine evaluated. That's c number I. So I think about what happens in general, and then I think about what happens in particular, and I see that the f of c is going to be 6 over 5 times cosine of ci, and because I'm using equally spaced subintervals, I'll omit the index I on the delta x. This is the definition of an integral. This is the integral of 6 over 5 cosine x with respect to x. To do the integral, I have to know the limits of integration, but we figured out what the a and the b values are. I'm integrating from 4 to 9. Again, make sure you understand that point. Antiderivative for cosine is sine. Evaluate at x equals 4, evaluate x equals 9. The exact value is 6 over 5 times cosine 9, sine 9 there, minus sine 4. In decimal, it's 1.4027 some odd. This limit would be really, really hard to do any other way, except because of its structure, because of the way it's laid out. I can easily see how to convert it into an integral, and once I've got it to this stage, that integral is easy. We learned how to do that in Calculus 1. This is going to be our trick for this entire chapter. We're going to have some problem that we're interested in. We're going to write it as the limit of a sum, and then by looking at it the right way, we will interpret that limit of sum as an integral. Then we use our integration tricks to get the answer. This is our one big trick in Chapter 7. Hopefully this is clear enough so that everyone can easily understand. At any time, if it isn't, get in touch with me on email or some other method, and I'll be happy to explain things more. Everyone, have a good day.